Hello, and welcome to this chapter on statistical inference. Today, we're going to just talk about how a sampling from a larger population can be used to predict or to generalize to the larger population. And that'll be for either a value or point estimation or a probability estimation or a frequency, the way I look at it. And so that's what we'll do in the first part of the chapter. And then for the second week, we'll look at hypothesis testing. So let's go ahead and get started. So the chapter starts out talking about a census collection. And a census collection collects data from every element in the population of interest. So it's the entire population that they're collecting information on. So you could think of this as a U.S. Census, where we go around every 10 years and collect all the data we can on the population within the United States. So there's a lot of, I guess, difficulties that go with collecting information from the entire population, or in this case, a census. One of those is because it's from everything, it's very expensive. It's very time consuming. When you do, if people aren't home, you have to go back. What if they don't give you all the information? That could be misleading. They don't report everybody that's living in the household. It can be unnecessary if you could generalize to that population, and a lot of times just because the population that you're trying to survey could be scattered everywhere, you can't get to them, it might even be impractical to get that information. So this is where statistical inference comes in, and we do that by using a sample data to make estimates of the overall population. So from those estimates, we can hopefully draw some conclusions about one or more of those characteristics of the entire population. So some names, some terminology. The sample population is a population from which the sample is drawn. A frame is a list of elements from which the sample will be selected. So your book looks at maybe a sample population is all the registered voters in Texas, and then the frame is a list of all the registered voters. We then go on to talk about selecting from a finite population or from an infinite population. Finite means that you know the number that exists in the population. Infinite population means you don't know the population number. So another term you should understand is a parameter, and that's a measurable factor that defines a characteristic of the population, process, or a system. So when you're sampling from a finite population, statisticians recommend selecting a probability sample when sampling from that finite population. And the reason being that a probability sample allows you to make valid statistical inferences about the population. We'll say more about that here shortly. So what you want is to gather a random size sample. So a simple random sample of a size n, notice this small n here, so that's a sample. From a finite population size, a big N, so that's the total number in the population, is a sample selected so that each possible sample of size n has the same probability of being selected. So what you're trying to avoid there is any bias. So if you're going to select, say, 50, then every time you select 50, everybody should have the same probability of being selected. I shouldn't say everybody. whatever you're sampling has the same probability of being selected. So here we have the example that's in the book. It's the EAI spreadsheet, and EAI is the Electronic Associates Incorporated. So what they've collected is data on their managers, their annual salary, and whether they've been through a training program or not. And so through the sampling process, they'd like to predict, can they get close to the population mean for annual salary, or the probability of showing that whether a manager has been through a training program or not. So remember, this is a finite sample. So sampling from an infinite population. So with an infinite population, you can't do a simple random sample because you can't get a frame consisting of all the elements. So what statisticians recommend is selecting what they call just a random sample. So again, a random sample of size n, the little n, from an infinite population is a sample that meets these conditions. Each element selected comes from the same population, and each element is selected independently. That is, you don't want to select an element that might be dependent on another element. So an example there might be, let's say you're selecting people whether they smoke or not. You've got a household that has a smoker in it. The likelihood of having another smoker in that household is significantly greater, and so then if you were to select more out of that, that's not independent and it's not random. So you need to make sure it's random, otherwise you're not able to generalize to the overall infinite population because you've biased your sample. So that's what you want to avoid. Now I just want to go back to the finite population and the EAI worksheet. So your book talks about using a function called rand. And you can do that. So it generates a random number between 0 and 1. If I double click this and I press the END button and I hit the down arrow key, it takes me to the bottom. So there's actually 2,500 observations here, or data points I should say. But notice that every time I might change something and hit enter, it changes the values over here. So what you want to do is do a Control-C, and you can either paste over the top or paste to the side, but this would be, let me do a paste, and we're going to do a certain paste special, and what I'm going to do is paste special is you want to do values, and what that does is it converts these functions into actual values that are on the screen. So notice that here are the numbers that were there, and you see the number that's generated, and here's the function. So this would be the set of numbers, if you're doing random numbers, that you would draw from at this point. So at this point, we could organize this set of numbers. We could sort it and say, okay, we're going to choose the smallest 10, and then we could get what's the average salary for that, what's the probability of having a training program or not. We can get a new set of random numbers, do that all over again, get another sample out of that, same size, and so each one can be picked for our sample. They're independent, they have the same likelihood of being picked because of the random numbers being generated to the side. So if you're following along in the book, I just wanted to make sure you understood how to get that random number and how to get it into an absolute number so that it's not constantly changing on you, and now you can do something with it. So to distort it, you would just select it all, and then you would go to data and you do sort, and you could sort on column. In my case, I'm going to do E here. We'll do the smallest at the front, and you can see that here are the smallest numbers. I could do a sample size of the first 10, then I do what the average, find what the annual salary average was and whether they had how many had a training program or not. And then we could see how close that was to the actual population. So right now you have all the data for this population. We could actually do the salary, and we could actually calculate whether they had a training program or not. But what we're trying to do here is show, will a sample size generalize to this overall population? So we're going to continue on with point estimations and how you go about calculating that. So we're going to have 5 slides of that. So to estimate the value of a population parameter, we need to compute a corresponding characteristic of the sample. So this would be a sample statistic. So the sample mean then is written as x bar is the summation of all the x's divided by n. So if we get all that, if we took a sample size of 30, we could see that we would have a sample mean of this amount. The sample standard deviation then is we look at each value, subtract the mean from that and square it. Then we divide by our n minus 1. So 30 minus 1 is 29. We get all that summation of that values here, divide by 29. Then take the square root of that, and that's our standard deviation. So we see that that's 3,384. We could also then do a sample proportion. That's what I was showing earlier in the training program. Let's say our proportion, out of our 30 sample size, we had 19, so that proportion is 63. Yeah, how well does that approximate what the overall proportion is? So calculating all of that is called point estimation. So we're calculating the mean, the standard deviation, and the sample proportion. So the sample mean is the point estimator for the population mean. The sample standard deviation, S, is the point estimator for the population standard deviation. So notice, if you have to do a little chart or something, notice how these symbols are different. So one is for the sample, one's for the actual population. Sample proportion has the bar across the top. It's the point estimator for the population proportion. Right, so again, those values obtained for these letters are called the point estimate. So if we look at our data, we could sort our data, smallest random numbers, take the first 30 that we have, and that would be our sample. From there, we can see what the salary is and whether they had management training or not. Then we would go back to here and calculate what our sample mean is, sample standard deviation, and sample proportion. Now, it may be that maybe all you want is the mean and standard deviation, and you're not looking at any proportions in your data. So they're just giving you the way you would calculate either one of those if that's what you're looking for. So if we run through that, we can see, like I said earlier, we can calculate the actual population mean for the annual salary, the actual standard deviation for the population's annual salary, and the actual proportion for the population that's completed the management program. Then we get our point estimates, and we can see that sample mean is 51,814. For this sample, that's fairly close. The sample standard deviation, a little low, and the sample proportion, a little high. But if we took a random sample of 30 and we did 30 of those, or maybe 50, we would see that the average of those samples would then very likely approximate these parameter values for the population. So then the question is once you have the sample, what can you say about the overall population? So some advice there is to have a close correspondence between the sample population and the target population. So the target population, or what I call the overall population, is what we want to make inferences about. The sample population, as it sounds, is just where we've gotten the sample from the overall population. So think about what you're doing. Did you make them independently? Have you tried to rule out all the bias you could before you could make that generalization? The next thing we want to talk about is the sampling distribution of your sample mean and the sample distribution of your proportion mean. And it's not really a mean, it's just your proportion. So when you're doing this sampling, you have a random variable, right, whose quantity you don't really know for sure. But you'd like to see how it's distributed. So that distribution is called the sampling distribution of X. And it's this distribution and its properties that enable us to make probability statements about how close the sample mean is to the population mean. And so that's the reason why we took some extra time to make sure you understood the previous chapter. So if I know the distribution, if it follows a normal distribution or a binomial distribution, I can then say, okay, I know that this proportion lies in this area of the distribution of this random variable. So let's say we went through the process that I showed earlier, and we did 500 simple random samples of 30 EAI employees. So we'd have all this, and we have a sample mean for each one of those random samples and a sample proportion for each one. Then we would get the grand mean and the grand proportion, that's what I would call it, for the overall. And we could actually then plot this as well to see what the distribution is. So notice we've got several bins here of the mean annual salaries. So we have a range. Remember, early on we talked about if you have too few bins, then you're not going to be able to explain the data enough. If you have too many, then you can't generalize enough. So here we have 9 bins, and we're going to look at this range here of the values of the annual salary. How many people did we fell into each category? So we got this frequency, and then we got this relative frequency. And that's just taking this 500 and divided into each one of these. We can plot that out, and we could get something like the following. So we could actually see that distribution. So we got the relative frequency here and the values of X here. And we would see that normally in the middle, then that's approximating the true mean of that population that we're trying to generalize to. But we don't know it for sure. That's in most cases. But in our case, using that data, we do know it for sure But again, they're just using that to show you how that if you do random sampling, it will approximate the general population distribution and the general population point estimators. Here we have the distribution of the proportion that of managers that got the training. So we see that. So when we look at that sampling distribution of X, then we know the sampling distribution has an expected value or mean, a standard deviation, and a characteristic shape or form, which we just saw in those graphs. The sampling distribution of X is the probability distribution of all possible values of the sample mean X. Think about that. That's a pretty important statement. That distribution is the probability distribution of all possible values of the sample X. So if we were to go back to here and draw a line, we could use that looks to be fairly normally distributed. We could say, okay, looking at that, I know that by my standard deviations, how many of the sample or population should be in each one of those areas. Right, so the expected value of a point estimator equals the population parameter. When that happens, we can say the point estimator is unbiased. So big expected mean is equal to the population mean, right? That mu there. So now for some calculations. The formula of the standard deviation of x bar depends on whether the population is finite or infinite. So if we use the following notations, right, the standard deviation of x or the standard error of the mean. The standard deviation of the population doesn't have any subscript on it. Small n is the sample size. N is the population size. So for a finite population, the standard deviation is equal to population minus n, population minus 1. Take the square root of that and multiply that by sigma over the square root of n. So this is the sample. If it's an infinite population, then standard deviation is equal to sigma over the square root of n. So the difference between those two formulas is what they call a correction factor, which is this value here. And that's for finite populations. So a lot of times that correction factor is very close to 1. So the difference between those values of the standard deviation for an infinite and finite populations is negligible. So a lot of times people will just drop this and just go with the other calculation. So if we look at those calculations, then we've got estimated standard error. So that's S over the square root of n. And we look at that value we calculated, n square root of 30. So it's 611.3. The true standard error is 4,000 divided by the square root of 30, so that's 730.3. So the difference between those two is due to sampling error. So if we did enough samples and we did the average of this, that would come very close to this true standard error. And remember, we got these values from a previous slide where we calculated those point estimates. So there's where the 3, 3, 4, 8 came from. We would do the same thing for that sample proportion. So some more on sampling distributions is that when the population has a normal distribution, then the sampling distribution of X is normally distributed. A lot of times you don't know what the population is going to be. Also, when the population does not have a normal distribution, the central limit theorem takes over to identify the shape of the sampling distribution of X. And though the central limit theorem says when you get a random sample of size n from the population, the sampling distribution of that sample mean is approximated by the normal distribution as the sample size becomes larger. So, if you don't think your population has a normal distribution, but if you take a large enough sample, then it approximates a normal distribution. And there are calculations out there that will tell you how large your sample size needs to be in order for you to get that normal distribution or approximate it, and then make generalizations about your population based on your sample that you got. So in this slide, what it's showing you is here's what the true population or distribution is for different types of population. What does the sampling distribution look like if you have a small n? So here they use 2, here they use 5, and then they went to 30. And so 30, you can see how it kind of approximates a normal distribution. So 30 is that magic number of what you want to have a sample size of at least that much in order to approximate that normal distribution. So using the data set we've been using as an example, then our sampling distribution of X sample and the actual standard deviation then is this. So we got one standard deviation is 700 plus or minus 730, two standard deviations is 2 times that, and then up to 3 times that. So what happens if your sample size increases? And so by example here, if we have a sample size of 30, we can see that standard deviation is around 730. If we increase that sample size to 100, that's the blue line here, we can see that the standard deviation becomes much smaller. And so we're not having as much dispersion. So that doesn't approximate what that standard distribution is for that population. So as your book says, a larger sample size will give you a higher probability that the sample mean falls within your specified distance. But you're going to have a smaller standard error. So we don't want to have too large of a sample size. And I'm going to pause right there, and when we come back, we will go ahead and talk about sampling distributions for proportions. It works very similar to the sampling mean we just covered.